Okay, good afternoon, everybody. Let's rock and roll. Today it's very eerie for me because I'm speaking to an empty room. I would really appreciate if you'd speak to me because this is honestly frustrating that you speak to no one. And I hope, yes, now everything is correctly turned on. You see, because previously I started recording the lecture has been recorded. The only problem was that there was no vision, no blackboard, just the sound. So it's completely useless. Luckily, the previous lecture was basically improving on what I already told you before, doing it for matrices or on graphs that are not necessarily finite. But today we will start with deliberating about graphs that are finite, because then we can have some useful conclusions about them. So let me write it down as a corollary. To be honest, I don't remember the corollary of what it is. Well, it must be, it's clear when you read the lecture notes. Let's see, it probably will be obvious during the proof. Anyway, the claim is the following. A finite graph has no loops if and only if its adjacency matrix is nilpotent. And let me immediately show you why we need finiteness here. Imagine the following graph, just an infinite path, like for compact operators or for arbitrary size matrices, okay? So of course, this graph has no loops. And when you look at this adjacency matrix, it's going to have ones above the diagonal. But it will go to infinity. And this operator is by no means, well, let me call it A of E, and this E. And this operator is by no means nilpotent. For any natural number n, A e to n is not 0. Anyway, I can recognize it as the unilateral shift that defines the famous step-less algebra. On a Hilbert space, it's just defined on an orthonormal basis that S of EI is by definition EI plus 1. And this is an isometry. That's definitely not anything nilpotent. Okay, so to characterize the lack of loops by the nilpotency of our adjacency matrix, we really need this graph to be finite. We really need this matrix to be finite. And indeed, if I have something upper triangular with zeros on the diagonal, surely an appropriately high power of this matrix will be 0. Okay, so that's what we're exploring. Okay, so let's prove it. This is not an immediate corollary. So for starters, look, if I take an empty graph, this is obvious. So we will assume that our graph is not empty. And of course, you can now debate what it means to take the adjacency matrix of an empty graph. Well, then you have to remember that the matrix is defined as a map from an empty set to something. Well, this is still a subset of a Cartesian square, and Cartesian square of an empty set with anything is an empty set. So sort of this nilpotency, this adjacency matrix will be just an empty set. And you can think about an empty set as a 0 map. So yeah, it's nilpotent. And of course, when it's an empty graph, it has no loops. It has nothing in particular, no loops. So just, for the sake of not removing some special cases, which, who knows, might be useful at a certain moment, I'm writing it down, but that's a boring case, right? So now we assume that the graph is non-empty. remember this theorem 115, which was proved by my daughter. So this is this theorem. Which says that a finite graph has no loops if and only if the space of all its finite paths is finite. Yeah. So by this theorem, yeah, so I'm just writing it down. The finite graph E has no loops if and only if the space of all its finite paths is finite. Okay, but now the letter which is the right-hand side of the equivalence.
Sure.
Yes?
I think it's not a unilateral shift what it represents the adjacency matrix. I'm like, this graph is the compact operators and do not contain the unilateral shift. It's rather like that.
No. But of course, I know that that's just a conclusion. Remember that this is completely two different things. It's a coincidence. Of course, there is no unilateral shift in compact operators. Unilateral shift is not a compact operator. But I made a jump. I mean, this is just done in terms of matrices, okay, and graphs, and that's it. This is what it is. And to be honest, this is not an operator on a Hilbert space.
Exactly, it's just a matrix representing the
this is just the adjacency matrix, and it has this property that it's not nilpotent. And then this is the second remark, sort of independent, that when you look at the unilateral shift and you look at its representation in this, say, an orthonormal basis for which it is a unilateral shift on some separable Hilbert space, then you can write the matrix in the same form. But that's, of course, this matrix here should not be interpreted as an operator in a Hilbert space. Yeah, I'm just telling you about the coincidence and how it is. I know immediately that this matrix is not nilpotent because I know that the unilateral shift is not nilpotent. Yeah, thanks for this comment. Okay, so the letter is equivalent or tantamount to the existence of a longest path. Of a longest path. And this is why I had to discard this empty set, right? Because if this is an empty graph, of course, there is no longest path. So this reasoning wouldn't work. But the moment I get rid of this empty graph, yes, even if I have just one vertex in my graph, it's already a path of length 0, but it exists, okay? And the argument works. But let's see. I love this word, indeed. If there is no longest path, so let's contradict it. But paths exist because it's not an empty graph. Well, then there are paths of all lengths. So there are infinitely many of them. And vice versa, again by theorem 115. If FPE is infinite, then there is a loop. So there is no longest path. Right, this gives me this equivalence. Because what they prove? Yes, if there is no longest path, then FP is infinite, and then if FP is infinite, there is no longest path. So this means that indeed this right-hand side statement, I mean, right-hand side of this equivalence is tantamount for non-empty graphs to the existence of a longest path, okay? So this is one reduction of a problem. It's half of a corollary proven. Yeah, I know, this is a corollary to previous corollary, 129. Because this is what we are going to use. We're going to use this corollary. Remember that A n E is the same as AE to the power n. So this is corollary 129. And this is the corollary to that corollary. So let's finish the proof. Next, if the length of the longest path is L, it might be 0. Then, by corollary 129, which I just spelled out for you, AE to the power L plus 1 is 0, right? Because if the longest path is of length L, and the corollary tells me that AE to the power L plus 1 shows me all paths of length L plus 1, but there are no such paths, so there are 0 of them, so this will be a 0 matrix, okay? So, which means that A is nilpotent. So I have it one way. Now, vice versa, if A of E is nilpotent, then there exists such n that AE to n is 0. Hence, again by corollary 119, sorry, 129, there are no paths of length greater or equal to n, so there exists a longest path. And again, I'm using the fact that this is a non-empty graph. And this ends the proof of a corollary. Well, the logic is obvious. First, I prove the equivalence of the lack of loops. Sorry, I prove the equivalence of the finiteness of the space of all finite paths to the existence of a longest path. And then I prove that the nilpotency of the adjacent matrix is equivalent exactly to the existence of a longest path. Okay, so this means that we are done. Because that's what we're supposed to prove, that no loops means, yeah, and of course, to begin with, we have the theorem that no loops means the finiteness of the space of all finite paths, then this means the existence of a longest path, and this means the nilpotency. So 3 steps in fact. Okay, no questions? So let's do something a little bit more involved, but still simple. And I'm still under the assumption that my graph is finite, again, for the same reasons, because it's about nilpotency, about being upper triangular. But this proposition might work for infinite graphs, except I don't quite see its usefulness, because if we cannot talk nilpotency for the reason I just explained, what's the point of having something upper triangular? I mean, the beauty of the proposition I'm about to state is that when your graph is finite, your matrix is finite size, then it's nice to know that you can always write it in some nice upper triangular form, because you have to take it to some powers to do computations. So it's nice to have it presented in a most convenient way. Okay, so the corollary just wouldn't work for infinite graphs. The proposition probably works for infinite graphs, but it would be a different proof. And I hesitated for a while whether or not to venture into proving something more general, but then I decided that it's useless. It's just not interesting enough. Okay? So let me stick to a finite graph in the following proposition. And anyway, I enjoy this proof. It's not difficult, but it's not completely trivial. Okay, so let E be a finite graph with no loops. Then we can always order E0 in such a way that its ordered adjacency matrix is upper or lower triangular with zeros on the diagonal. I hope you can read it. Yes. Yeah, let E be a finite graph with no loops. Then we can always order E0, the space of vertices, in such a way that it's ordered, I mean, like the graphs, adjacent matrix A of E is upper or lower triangular with zeros on the diagonal. Okay. And now before I show you a proof, let me remark that this looks very much like some normal basis theorem. You know from general linear algebra that if you take any endomorphism of a finite dimensional vector space, that you can always choose a basis in which, or the ordered basis, in which this endomorphism will have a matrix which will be partially diagonal and partial we have is Jordan blocks. So Jordan blocks will account for nilpotent parts and the diagonal part for the rest. But you see, in this linear algebra theorem, this is a beautiful theorem, very important one, you are using any linear transformations between one basis and another. Whereas here, the only linear transformation I'm allowed of my basis is a permutation. So that's a different story. I'm telling you that I can always permute my basis in such a way that my matrix will be upper triangular. This is not an arbitrary linear transformation. So this proposition doesn't, strictly speaking, follow from this linear algebra theorem. Although, indeed, you can take for your finite dimensional vector space just a linear span of E0, where K is a field. And then this will be something very much in the spirit of this general algebraic plate. Okay, but let's do it in a graphy way, because this is what we have to do. To be precise and complete. So again, as before, as in this corollary. So for starters, part of my glove gets into the chalk, and this is not so easy. Okay. So for starters, it is obvious for the empty graph so we assume E is non-empty. And again, this is just a question of an interpretation. If a graph is empty, then its adjacent matrix will be the zero matrix, in the sense that to no element in an empty set you assign the zero. So this is a matter of interpretation, but by convention we can just say that this is true. Okay. And in the proof, it will be very important to know that E is non-empty. Again, as in this corollary, an argument doesn't work if you work with an empty set. Okay. So we assume that E is non-empty, so it means that the set of vertices is non-empty. The set of vertices might be empty, but the set of vertices is definitely non-empty. So we assume this, and an order well, this is a partial order, and define the following natural partial order. Well, partial order in E0. So V is less or equal to W if and only if there exists a path from V to W. Okay, so if, say, this is my graph, V prime W U. So you see V is less or equal than V prime, V is less than equal than U, but V and W are unrelated. Okay, it's just so that you have it in mind. Now, this relation is evidently reflexive and transitive. Okay, this relation is evidently reflexive and transitive. Well, it is reflexive because a path from V to V is V itself. It's a length zero path, but it is a path. And when you have a path from V to W and from W to U, then by concatenation, you have a path from V to U. So these two properties are obvious. But yeah, well, now the reason why it is, so this would be a preorder, but this is also antisymmetric due to the Lego loops. Well, indeed. If V is less than equal than W, and W is less than equal than V, then there is a path from V to V via W. Which is a loop unless V is equal to W. But I have no loops, so V must be equal to W. And this is exactly the antisymmetry of the relation. So we have a partial order in our finite set of vertices E0. So it's a poset. Okay. So that's the first part. It's not convenient to write at the bottom of the blackboard, so let me switch to the next one. So next we are defining the following set. Subset in the set of vertices. So let F naught be by definition a set of all such vertices that have a property that they are at the very bottom in this order. So if V is less or equal than, if W is less than equal than V, this implies that W is equal to V. So if you want a picture, imagine here is your finite graph. Something like this. So here my F naught would consist of these two vertices because nothing maps to them, okay? The only vertices that are less or equal than these two vertices are these vertices themselves, right? That's not true for this vertex, for that vertex, okay? So the idea is that I'm going to take sort of the lowest vertices and chop them off. Then I consider the graph without these vertices and without the edges starting from these vertices and repeat the construction. Again, look at the lowest vertices and so on and so forth. So this will give me a decomposition into subsets, these joint subsets. And these subsets will be among themselves already totally ordered by our partial order. And in these finite subsets, I will be able to introduce any total order I want, because in this relation, elements in this set are unrelated by my partial order relation. So that's the idea of a proof. Yeah? I'll inductively define then F1, F2, and so on. But each time it will be the idea of taking all the vertices that are at the bottom of the graph with respect to this relation. But first, let's see that F0 is non-empty. Okay. So by contradiction, suppose that F0 is empty. Then, as E0 is not empty, remember we assume that E is not the empty graph, we have.
Sorry?
Yes?
We can only read until the suppose that.
Okay, okay. So you know what? Thank you very much. I'll just draw a line here.
Yes, thank you.
Yeah, thank you. I'm sorry about this. But this is important. Suppose that F0 is empty. Then, as E0 is not empty, we have the following statement. Well, what does it mean for F0 to be empty? It means that for all vertices V in E0, this implication is not satisfied, which means this is not true and this is true. Okay. So for every V in E0, there exists a vertex W such that this is true and this is not true. Okay. So this is what would be implied by the emptiness of F0. But this contradicts the finiteness of our set E0 because we have no loops. So let me write it down. So since there are no loops, it yields an infinite sequence of vertices contradicting the finiteness of E0, contradicting so we can conclude that F0 is not empty. Right? Why is it infinite? Well, so I have my, I pick up absolutely any V in E0. Then I find a different vertex W, which is less than V. Okay. But then I apply W is also, a vertex in E0. And this is a quantifier for all vertices in E0. So for a W, now again, I can find a vertex different from W, which is less than W. And of course, if we allowed loops, then this, if you want, W prime could be equal to V, but we do not allow loops, right? If any, so okay, this is my vertex V, and I have a W which is different from V, and I have a path from V to W. But then the same is true about V. There is about W. There is a vertex U with the same property. But now you can ask, well, but why U of course must be different from W, but why is it different from V? Well, it's different from V because if it weren't, we would have a loop. So we step backwards and backwards, and we can never come back to any vertex that we already had before, because then we would have a loop. That is why we have an infinite sequence of vertices, which is not allowed by our assumption. Okay, so this is very important. F0 is non-empty. But it's intuitively clear, if you take any finite graph, well, then obviously you must have pure sources somewhere, as you must have pure sinks somewhere. Okay? But this is a formal argument. Now, there is a most important step. And again, I will do it on the other blackboard so that it's clearly visible. Because now I want to define things inductively. So we can define inductively Fn plus 1 So this already gives you the idea of what's going on. And now I'm modifying my set of vertices. I now disregard these vertices which are already at the bottom and look at all other vertices. Okay, and then I'm applying the same construction. So as promised, I define Fn plus 1 as the set of all vertices V, but now no longer in E0. I have to get rid of all vertices that I already considered before. So I have the union from I equal 0 to n of all Fi's, okay? And then my vertex W, again, must be in this set, but to write it in a shorter way, I'll write it as W not belonging to this union. And if W is less or equal than V, well, then this implies that W is equal to V. So that's, formally speaking, what I told you I'm doing. I take away all these lowest vertices in my partial order. I remove them. Then I consider the set with all these vertices just mentioned removed. And then apply this construction again. So here both V and W are in E0 less the union from I equals 0 to n of Fi's. Okay? So this gives an inductive definition, and then the implication is the same. I have V and W in the subset of E0, and then for this subset, if V is less, if W is less than equal than V, then V must be equal to W. So again, I'm taking in this subset, I'm taking the vertices which are the lowest with respect to my partial order. Okay? And now, reasoning exactly as before, we conclude that if this set from which I take my vertices is non-empty, this implies that Fn plus 1 is non-empty. That's exactly the same reasoning. Okay? But because each time I'm taking away more and more vertices, and the set of vertices is finite, at a certain moment, this procedure has to stop. At a certain moment, this preceding statement of my implication must be false, which means that it must be the empty set. which means that E0 is equal to the union of all Fi's. Okay, so let me write it down. So therefore, since E0 is finite, there exists an M such that E0 is equal to the union from I equals 0 to M of Fi. Okay? And this is exactly what we wanted to achieve. That's the first, well, this is the second part of the proof. We have one more to go. I hope everything is clear up to now. The most important is inductive definition of Fn. Okay? And then, because of finiteness of E0, we finally have the decomposition of E0 into the union of all Fi's. And now let's see that this is in fact the disjoint union. This is pretty clear from the construction, but let's formally write it down. Furthermore, by construction, we see that if I is different from J, then the intersection of Fi and Fj is empty. Well, indeed, if I is equal, different from J, then one of them is bigger, then we have, say, I bigger than J. So this means that when we take Fi, if you look into the very definition, then all the vertices in Fj are removed from the pool of vertices from which you choose vertices for Fi. So the intersection is empty. So this is in fact the disjoint union. So E0 is a disjoint union from I equals 0 to M of Fi. So we really have a nice decomposition. Now it follows that any total orders chosen for Fi's combined with the partial order we already have, turn the latter into a total order. Remember, total order is a partial order with the property that all elements are related. Okay. So basically, what I'm doing here, the vertices in particular Fi's are unrelated by my partial order. So I relate them artificially any way I want. You can always introduce total order inside a finite set. Okay. Just by enumerating the elements. And then the combination of these two things gives me the total order globally for all E0. Okay. Now I want to see that with respect to this total order, I have the total order I just defined, constructed if you want. my adjacency matrix will be indeed upper triangular. Okay. Okay, so let's prove it. So now, because there are no loops, N1 PW is 0 for all VW in Fi and for all I ranging from, 0 to M. Well, if W is equal to V, then of course there is no edge from V to V because there are no loops. Now, why is it? I told you already, but let me now argue why it is the case. Why no two different elements in Fi are related? Let's see it. Assume that they are related. Well, then we just get into the contradiction with the definition of Fi, right? Imagine that I have two vertices V and W, and they belong to Fi. If they are related, this means that there is a path, okay? That they are, since they are in Fi, well, they satisfy this assumption of a definition that they are from the right pool of indices, both of them, okay? So since they are both of them from such a set of that form, the right set of vertices, it means that this implication applies to them. And if they were related and different, well, we get a contradiction. So this shows that if I have any two different vertices in Fi, then they are unrelated. There is no path from one to another. Okay? So in particular, there is no path, there is no edge. So N1, remember, this is our notation for the number of paths of length written here, which is 1, which is an edge, from a vertex V to a vertex W. So this is the number of edges from V to W. Okay, so next we want to prove that if I is bigger than J, that there is no path from index in Fi to an index in Fj. That is upper triangularity if you want. So no loops immediately guarantees that we have zeros under the diagonal. So next, I claim that N1 PW is 0 if V belongs to Fi, W belongs to Fj, and I is bigger than J. Okay, let's see it. So indeed, N1 VW positive implies that V is less or equal than W, and we'll quickly get a contradiction. Just let me erase the blackboard. So hence, as V is in Fi by assumption, and I is bigger than J, I know that Fi is a subset in E0 minus the union, say, from L equals 0 to J of F else. Right? Remember, this is by the inductive construction of Fi. We choose these vertices for a bigger I first by removing from the set of vertices where vertices belonging to F's with lower indices are removed. So in particular, because J is less than I, well, everything from L equals 0 to J is removed from, well, in fact, if I is containing 0, less the union from L equals 0 to I minus 1. But I minus 1 is greater or equal than J. So this holds, okay? But this means that this is in the pool of vertices from which you choose vertices for Fj, okay? Because you choose vertices for Fj from something even bigger. You take this union from L equals 0 to J minus 1. I didn't write it because we might have J equal to 0 and then there's no J minus 1. And then this is the whole E0, okay? But you know what I mean. In the definition of Fj, we allow vertices from this set to test the implication, okay? So if we have that V is less or equal than W, then because V is in the right subset, and this is of course due to I bigger than J, well, we obtain P equal to W, which contradicts disjointness of Fi's. I mean, it already contradicts. Yeah, okay. I think this is the right way. Okay, so one more time. If N1 VW is positive, then it means that there is a path from V to W, so V is less than equal than W. But now V is from the set of vertices that witness the definition of Fj, because I is bigger than J. So this means that under this assumption, because V is in the right subset, this implication must hold true. And the implication says that V must be equal to W. And that's impossible because V is in Fi and W is in Fj, and these are disjoint sets. Okay, so we are done. Well, I might add for I bigger than J. Okay, so consequently, we are done. The fast ordered adjacency matrix is upper triangular with zeros on the diagonal. Right, because this is what we just showed. If I have two vertices in the same Fi, then the number of edges from one vertex to another is 0, so nothing here. If I have a vertex which is higher in this total order and another one, so if Fi, another one is Wj, is in Fj, then again, the entry, the ijth entry, the appropriate entry labeled by these two matrices will be 0. And that's exactly the condition for being upper triangular. So in other words, in this total order, if V is greater or equal to W in our total order, then this means that N1 VW is equal to 0. And this is exactly the condition for being upper triangular. And now the lower triangular case, is obtained for the opposite order. Obtained for the opposite total order. Right, so you can say, I don't know, A is curly less than equal than B, if and only if A is greater than equal than B. And then you just change your inequalities, and what is upper triangular will become lower triangular. So this ends the proof. I quite like the proof because it's nicely conceptual. It's not too difficult, it's not too easy. It's just a very nice combinatorics. Any questions concerning this proof and the proposition? Nope. Okay, so we can continue. Yeah, we still have like half an hour. Now I want to return to counting paths of length k in graphs with n edges and no loops. And this is the last part before going to the structure of graphs. And the reason why I want to do it is because I want to show you that this big K theorem can be reformulated in a way that works for real numbers. I can reformulate it into a theorem about non-negative real number matrices. And this theorem was recently proven by Alex Kivasitu. So it's kind of funny how combinatorics of graphs led to some theorem which is pure linear algebra. So that's what I intend to do in the remaining half an hour. I write it as a corollary. Well, basically corollary of this K theorem. These pieces of chalk get used up so quickly. And then it's very tough to write with a small piece of chalk when you wear gloves. Okay, so let script En denote the set of all graphs with n at least one edges and no loops. Then for any k ranging from 1 to n, it makes sense because n is at least 1. The maximum over all graphs in the set script En of the following number. We take the adjacency matrix AE of our graph E running the set script En. We raise it to the kth power. We take its matrix element VW. So now it's a natural number. And we sum over all VWs in E0. And guess what? This is equal to our combinatorial number P and K. Remember in the theorem 120, we defined this combinatorial number Nk for n at least 1 and k ranging from 1 to n. Okay? If you don't remember, it doesn't matter because we are just reformulating basically the theorem 120. So whatever was in this theorem is in this corollary. Okay? So this is what we want to prove. Well, actually, I can just, let me not write the proof. Let me just talk the proof, because this is just writing plain English sentences on the blackboard. It's quite awkward. It's nice to write a formula, but if I just write sentences, my horrible handwriting, I feel frustrated myself. And basically, it's by citing the corollary. So writing numbers on the blackboard when you don't see which corollary it is, it's not quite right. So first, note that since the number of all edges is finite, the above sum is always finite, okay? So first, if you look, how do you multiply matrix with itself? Well, you take the entries, so you have a matrix M, and you multiply Mi1, I2, Mi2, I3, and so on, and finally you will have Ik plus 1, okay? So you sum over all these indices I2, I3, up to Ik. This will give you enters in here, but there are only finitely many edges. So this means that if you take the adjacent matrix AE, it has finite support. Yeah. If there are finitely many edges, then there are finitely, there are just finitely many edges. So the sum, if you forget the k, the sum of all entries is equal to n. And since we are dealing with natural numbers, at most n entries can be non-zero. So they're only finitely, so these sums are always finite. And then at the end, well, what you do, you also sum over I1 and Ik plus 1. But again, by the same reason, all these sums are finite, because there will be only finitely many entries in this potential infinite matrix with non-zero values. Yeah, so we have a finite sum, so it always exists, always makes sense, okay? Because a priori, you can say, wait a second, you didn't assume it's a finite graph, and you have such an infinite sum. So what does it mean? Well, in fact, this is a finite sum because we fixed the number of edges to be n, and these are matrices over natural numbers. This argument wouldn't work if it were a real matrix. Okay, so that's the first one. Now remember, we had this lemma 114, which was telling us some sort of sketching the proof instead of writing full English sentences. We had this lemma telling us that if I have n edges in whatever graph, then the number of all paths of length k is at most n to the power k. All right? So this means that it satisfies the assumptions. So that's the space of all paths of length k is finite, yeah, in any graph with fixed number of edges. But this means that our adjacency matrix satisfies the conditions of corollary 130, which we redid, which was redone a week ago, which was telling us that indeed the adjacency matrix to the power k is the same as the generalized adjacency matrix whose entries are all paths of length k from one vertex to another, okay? So that's if I look at if I remember this lemma, I see that the assumptions of appropriate corollary are satisfied. So yeah, but actually, sorry, maybe yeah, okay, and yeah, indeed. So this counts. Sorry, so this counts the number of all paths of length k, right? That was the corollary. It needed an assumption that it works only for graphs with a property that for any pair of indices, the space of all paths of length k is finite. Well, since the space of all paths of length k period is finite, then the assumptions are satisfied. So I can still claim that that sum counts the number of all paths of length k. Okay. And the final argument is, well, I'm taking the maximum over an infinite set. So it's suspicious. How do I know it exists? Well, now I can use my theorem, because there are no loops. This is what we assume, right? Now I'm using these assumptions. I can use my theorem that 120, right? That this number of all paths is bounded by P and K, and moreover, the bound is attained for appropriate graphs E. And I see I have a typo in my notes. Okay, so if these sums are always bounded by P and K by this big K theorem 120, and the bound is attained, well, then the maximum over this infinite set is just equal to P and K. Right, so this ends the proof of a corollary, which you should treat as a reformulation of theorem 120, basically. Okay, now I have a remark, which is kind of cute. Well, I want to argue that in fact we are only dealing with a finite set here. So, as was at the beginning of the proof of this big K theorem, well, we can immediately throw out all vertices which are not in the image of the source or the target map, as they do not contribute anything to counting paths of length k, because k is assumed to be at least 1. And then once the set of vertices is finite, there are finitely many elements, or finitely many such graphs. Okay, so it's a remark. There are finitely many graphs with n at least 1 edges and whose all vertices emit or receive an edge. Okay, indeed. For any such graph E, we have that E0 ranges from 1 to m, with m less or equal than to n. You see, if I have n edges, then I have at most n different sources, at most n different targets. And if they're all different, then my set of vertices is at most 2n element set, but not bigger. Okay. Now, remember that the source map and the target map are actually subsets in the Cartesian product of E1 and E0. So the number of all such graphs is limited by, well, by the choices we can make, right? Remember, a graph is a quadruple, so E1 is fixed. It has all the n different edges. Well, E0 is not fixed, but the number of all possibilities is at most 2n. And here the number of all possibilities, so I take the set of all subsets in this Cartesian product, and this has n elements, this has at most 2n elements. So this will be bounded by 2 to n times 2n. And I do it twice, because once I do it for the source, once I do it for the target map. And when I multiply it out, I have n times 2 to the power 4n squared plus 1, which is a finite number. It's huge, and of course, it's very far from being optimal. Say when n is equal to, well, I'm not telling you that you can have 2 to the power 17, actually then, and 2 to the power 18 different graphs. No, it's much less. Yeah. If I look at graphs with 2 edges and no vertices which are beyond the source or the images of the source and target maps, then this is definitely less than 2 to the power 18, okay, which is a huge number. But, well, I wanted to somehow show you that this number of possibilities grows very fast. I know this is very suboptimal and naive estimate, but somehow we should assume exponential growth of the number of graphs with n. So that's why this theorem 120, which counts all paths of length k, is so interesting, right? Because we're dealing with a set which is huge. If I take n equal to 1 million, the amount of all graphs I'm interested in is enormous. Even, of course, after the truncation, throwing out all the indices that are vertices that are irrelevant, vertices that are not in the image of the source of the target map. Okay. Now, a very, very important step. I want to show you that indeed there is sort of an equivalence between adjacency matrices and graphs. Well, let me focus on the finite case. So that's the end of the remark. Let me now continue on this blackboard. And all the properties about graph I'm interested in can be recast in the language of its adjacency matrix. And this is a very important observation. Observe that if I take any matrix A, finite, of size n, with entries being natural numbers, then I can always construct the graph such that this will be the adjacency matrix of this graph. And here I'm sweeping under the carpet distinction between ordered adjacency matrix and non-ordered. This is a finite set, and you can always order it by a total order. Okay, then it is the adjacent matrix. Of the graph that I denote as E of A, and which is defined as follows. So first, the set of vertices, sorry, is by definition the set of numbers from 1 to n. Now, so this is EA0, EA1. Well, this is the union of over ij's in E0 of EIJs, where EIJ is the set of AIJ many different edges from I to j. Okay, so I take any two vertices, they are just numbers from 1 to n, and I want to count all edges from one number to another. And I have exactly as many edges as the number A of j, which is a natural number defining my matrix from my matrix as a matrix entry of A. Okay. And also I have to define the source and the target map. But this is completely obvious. It's defined by the formulas as follows. I take any vertices ij. I take any edge in Eij, and I say that if E is in Eij, then S of E is equal to I, and T of E is equal to J. Okay, so this defines the graph EA, and let's do an example. For n equals 3. So in particular, for n equals 3, we have, well, we have three vertices, 1, 2, and 3. And we have A11 many loops from 1 to 1, A22 many loops from 2 to 2, and of course A33 many loops from 3 to 3. Now I have A1 too many edges from 1 to 2. I have A21 many edges from 2 to 1, and likewise for other pairs of vertices. So from 1 to 3 is A1 3. From 3 to 1 is A31. From 2 to 3 is A23, and from 3 to 2 is A32. Okay? And in general, it is clear that these are mutual inverse constructions. So the adjacency matrix of the graph of a matrix A is just a matrix A, and the graph of the adjacency matrix of a graph E is equal to E. That's just a tautology by the way we construct it. Okay? So at least for finite graphs, finite size matrices, we have complete equivalence between adjacency matrices and graphs. I'm not saying that it's just for finite graphs, but I'm going to reformulate my theorem 120 for finite graphs, so that's enough. And when you generalize it to real numbers, then it's better to have a finite size matrix.
So I think formally the second equality should be an isomorphism.
Yeah, surely. Yes, this is a good point. It's a question of tradition. It is customary to write down a canonical isomorphism as equality. Okay, so this is very common, I mean, especially in K theory. Otherwise, you basically almost never write an equality. When you compute something in homological algebra and then you write, okay, some homology group of blah, blah, blah is equal to Z. Well, this is not really equal because you have to specify the generators. This is some abstract construction given by topology or operator algebras, whatever. And here just write numbers. So you should really write things like generator and stuff like this. And even then, it's just an isomorphism, not an equality. But as long as our isomorphism, our identification is canonical, obvious, natural, then we can write equality. Yeah, but I agree. This is yeah. I mean, here you can claim indeed this is just a matrix. I start from some set of numbers and I come back to the same table of numbers. So here I can write the identity, but here when I do it, I have just the same looking graph, and I can just save it via isomorphic. Yeah, I fully agree. I have no problem with changing to an isomorphism. You see, this is why when remember we defined the equivalence of categories, it was very important that when you apply two functors in a different order, what you get is a natural isomorphism, not just identity, because it hardly ever happens that you have an identity. Typically, what you get is a natural isomorphism. Okay, now I have one more corollary, which reformulates my theorem 1. Oops, I don't want to erase this. EA of E is isomorphic with E. Okay, I want to erase this and write a corollary. So you see in this theorem 120, the K theorem, K-path theorem, we didn't assume that the graph was finite, but this was not very important because by removing all these vertices that were not in the image of the source of the target map, we do not change at all the space of positive length paths. So from the point of view of this theorem, it's irrelevant. We can reduce ourselves to this finite set of graphs. Well, this is finite by the remark which I erased. And without really losing any generality, we might as well assume that every vertex receives or emits an edge. Then we are down to earth to finite matrices and to finite graphs. And for finite graphs, I can write everything beautifully equivalently in the obvious way in terms of adjacency matrices. And this is what I want to do. So yet another corollary. So let n be a natural number greater or equal than 1. And let an, script an, be the following set. This is the set of all finite but arbitrary size matrices. So I write it as the union of our positive integers of the matrices Mn with values in n. Now I take matrices satisfying the following three conditions. One, two, and three. And now I spell out these conditions. So one, well, we want to consider graphs with n edges. So what does it mean? But then I take the sum over all ij's of aij that's just equal to n, right? And this is tantamount to EA having n edges. I remember because the entries of the adjacency matrix are defined by the number of edges from one vertex to another. So when you add up all entries, you'll have the number of all edges. And we want it to be equal to n. 2, A is nilpotent. So you see, for instance, here I need finiteness. If my graph is infinite, if my matrix is infinite, then no loops doesn't mean nilpotent. And also it doesn't mean that it somehow converges to 0 when you take n going to infinity. This is what I showed you with this unilateral shift example, this graph of the compact operators. So, but when we are finite, these are corollaries from which I started the lecture today. We know that this means that the graph EA has no loops. Now 3. And now I want to write down that every vertex receives or emits an edge. So I write that for any I, the sum over all j of aij plus aji is positive. Right, so this means that when I fix my I, at least one of these numbers will be positive for some j. So this means that there will be an edge which is received or emitted by my vertex I, okay? So each vertex of EA emits or receives an edge. Okay, so these are our assumptions. So what's the claim? Well, you can guess it. If you forget 3, that's basically, these are the assumptions of theorem 120, and this is, if I take an appropriate maximum of appropriate sum, it will count all paths of length k, and the result will be Pnk. And the third condition is just to remove zeros from my matrix, which do not contribute to anything, and just blow up the size of matrices. Okay, so under these assumptions, I claim that for all k ranging from 1 to n, capital N, the maximum over all matrices running the set script an of the sum of all entries, I write all ij, and here I have my matrix A to the power k, and I take its ij's entries, and the maximum of all such sums is Pnk, a combinatorial number from theorem 120. And indeed, it follows from all the things that we worked out. Yeah. Because basically what I'm doing, I'm taking a graph with n edges, no loops, and such that every vertex emits or receives. Right? And then I know that in such a case, the maximum number of all paths of length k is Pnk, and I know that this bound Pnk is achieved. So this is true. And in fact, with these conditions here, when you combine that this sum is equal to n, you will see that this is in fact a finite set. If you combine 1 and 3, you will see that you'll have at least, at most, finitely many vertices. So the size of a matrix will be limited. I'm writing it here in such a way on purpose. This is done on purpose. It might look awkward for natural numbers, but well, this is the punchline, the last thing I want to say today, but it sort of ends the chapter. And then we are moving forward to the structure after Christmas. We move, in the new year, we move to the structure of graphs, which is then directly relevant to Leavitt path algebras and graph system algebras. So sort of this ends the combinatorics, but it ended with a beautiful and completely unexpected theorem. So you see, when we deal with natural numbers, okay, we know that somehow here the size must be limited. So this tells you that the support of a matrix A is finite. Otherwise, the sum would not be finite. Okay, because all entries are non-negative. So all positive entries would be would add up. You can have at most n non-zero entries because any positive entry here is at least 1. Yeah, so it's supported on at most n places. Okay, and now by this condition, basically you don't allow the case where you have everywhere zeros. There must be something positive somewhere. So when you combine these two, you can conclude, well, wait a second, in fact, the set, the size of my matrix is limited. Yeah, it's limited at least by 2n. And this is the argument that we had before. If I have a graph EA, then it can have at most. So with this property that each vertex receives or emits, and I have n edges, then I have at most 2n many different vertices. So the size of this matrix is at most 2n. But it doesn't work for real numbers. Okay, so this is just a reformulation, yet another reformulation of theorem 120, but now purely in terms of matrices over natural numbers. I can just erase my comments about graphs, and I have a non-trivial, unexpected statement about matrices with entries in real numbers. Okay. But now let's end this combinatorics by a theorem, which in Colorado was phrased as a conjecture, but was recently proven by Alex Kirvasitu. And that's the new paper that I put on the Moodle page. This is a paper where this theorem is proven. So now let n greater or equal than 1 be a real number. Not natural, a real number. And let the set of an be defined as follows. Well, it's completely analogous. I'm just changing n for r. So these are all matrices which are finite size over the semi-ring of non-negative real numbers. So they're arbitrary size, but finite. And here, this is important because here, the size of a matrices is not limited. A can be arbitrary size matrices, but finite size. And of course, satisfying the conditions 1, 2, 3, which are exactly the conditions written here. I mean, these are some numerical conditions. I can now say that aij's are non-negative real numbers. I assume that n is a real number greater or equal than 1. So all this makes sense. I can speak about nilpotent matrices of real numbers. I can add real numbers. I can still write inequalities between real numbers. So conditions 1, 2, and 3 make perfect sense. So this set an is well defined. And then for any k ranging from 1 to the maximal integer part of n, so k is a natural number. It's at least 1 and not more than the biggest integer that is inside n. And now my set is really infinite. This set an is really infinite. So instead of max, I take supremum. I mean, the other set was also infinite, but in fact, this max was the same as a max taken over a finite subset. So I could write max. Here I want to write supremum because this set is genuinely infinite. I mean, the size of matrices is not limited. So I take supremum over the set script an. And of course, I take the same number. So I take the sum over all ij of a to the power k and enters ij. And you see, I cannot just write explicitly the set of indices simply because I don't know the size of a matrix, right? So if the matrix is of size n, then I and j range from 1 to n. But the notation would be too awkward to write it down, especially when it's really obvious what we are talking about. That sum is really over all indices, numbering all 8 entries of my matrix a to the power k. So now this is asserted real number. And well, if you read my updated lecture notes, then you know what it is. But if you haven't read it, what's your guess? What's your guess for the right-hand side? Should I write P and K again, or will it be something different? Any ideas? Remember that the basic idea behind theorem 120 is that you have edges as equally distributed among vertices as possible. But over there, we were limited by natural numbers. So it could happen that the number of edges is not divisible by the length of a path, of paths that we are interested in, right? K need not divide n. So we could not just say that between any two edges, we will have exactly the same amount, and the two vertices will have exactly the same amount of edges, simply because then this would lead to fractions, and we would have non-natural number of edges between two vertices, okay? But now this obstruction is gone, now that we talk real numbers. Remember that entries of our matrices stand exactly for the number of edges between vertices. And now, because we declared these entries to be real, we took these entries to be real, well, basically what we are talking about here in this theorem is sort of funny graphs, or we can say weighted graphs, where there's a real number that tells you that there's a square root of pi edges from 1 to 2. All right? So now there's no such an obstruction. When we want to make an even distribution, well, we just do it. So the number on the right-hand side is n divided by k, and that's all right. It's just a real number to the power k. And this is quite a surprising theorem that you wouldn't expect or cook up without the combinatorics of graphs. And written as such, it has nothing to do with graphs, unless you have some generalized idea of a graph where you have weights, real weights written next to edges. And then it's fine. And remember, we had to, this was Jacek Hajac who was showing this to us. If we have two numbers, x and y, that add up to some number n, okay? Then in order to maximize x times y with this bound, we must take x equal to y equal to n half. So the supremum of this is equal exactly to n half squared. So I have x equal to n divided by 2 and y equal to n divided by 2. This is what Jacek was showing. So this is the same, but now we have a bound for the sum of k guys. And you can guess very much the same proof will show that the multiplication of all these numbers will be the biggest when they'll all be equal. And this is what is reflected in this theorem. Okay, I stole 15 minutes of your time. So we will resume at 2:15, but we'll finish as declared. And then I will do it the other way around after Christmas in the new year. We'll have 15-minute longer recitation class, and we'll have 15 minutes shorter lecture. But I really wanted to come to this point and be finally done with the combinatorics of paths. Okay, so this ends the chapter of paths. That's it. I have no more to say at this point. And now I want to move to the structure of graphs, where we'll see what are hereditary subsets, saturated subsets, what are breaking vertices, and what can we claim about intersections and unions. So from now on, we'll be studying properties of graphs that are directly related to Leavitt path algebras and graph sister algebras. Are there any questions concerning today's lecture? I'm kind of disappointed that none of you guessed it. Or maybe you guessed it but didn't bother to speak up. But this is, I also want to draw attention to the fact that you cannot treat, strictly speaking, this theorem as a generalization of our theorem 120, right? Because this is not a number P and K. Situation is slightly different. And of course, all such matrices over natural numbers are also matrices over non-negative real numbers. So this set is a subset here, but somehow, well, not somehow, the right-hand side is numerically not the same in this theorem as it is in our theorem 120. And that's because now we allow fractions. And as the last remark to end this lecture, let me mention that there is a concept of quantum graphs. I know that 4 of you attended a talk by Christian Vogt at my seminar on quantum graphs, and it is again defined purely in terms of adjacency matrices. It's now that what I did in this theorem, what we did, we replaced natural numbers by real numbers. So it was over natural numbers, and we went to non-negative real numbers. But basically, what happened here is that this was replaced by sister algebras. So now entries of my adjacency matrix were in the numbers, they're operators on a Hilbert space. So I don't know, maybe eigenvalues of such an operator, the measurement of such an operator would give the number of edges from one vertex to another. So vertices are somehow not quantized, but now the number of edges from one vertex to another is given by an operator. But that's very much in this spirit. And the story of quantum graphs is brand new. This is really brand new mathematics. It's quite exciting because it's related to quantum computing and quantum cryptography. So for these of you who, the 4 of you who attended my seminar, you know what I'm talking about. And if you're interested in, you can just go to my YouTube channel and watch this video of Christian Vogt. Okay, enough talking. We resume at 2:15. I stop recording.